What happened? I hope I did not log off. Hello? Can you hear me?
Yes, ma. Can hear you, ma.
Okay, okay. All right, you're all welcome. It's exactly 5. So we are going to start off. Perhaps others will join later. I don't know, those of you that are here, did you join during our last facilitation class? Hmm?
Ma, is it that of the periodic table? Yes,
Yes, ma.
Okay, because why I'm asking is for the sake of those who were not able to join during our last facilitation class, just to inform you that the first class we had and the last one, the one we had, the second one, I've pasted the link to the recording of that, of both classes. So the virtual learning environment for this course, so that those who miss can go back and listen to it. The link is there, the password is there. So today we've done module 1, unit 1 and 2. We are going to do module 1, unit 3. Like I told you people, that module 1 is a bit kind of much because it's up to 6 units and all that. So today we are going to look at unit 3, and that unit 3 is talking about rules governing filling of electrons, then electronic configuration, then electronic configuration of ions, and then distribution of elements of the periodic table into blocks. So we're going to look at what these topics are talking about. Basically, that unit is divided into 3 sub-headings. So at this point, I'll be sharing my PowerPoint. But before I do that, from our previous classes in our O-level, we have idea about electronic configuration, how electrons are distributed into how the number of electrons that makes up. Now, some people are making noise. I don't want to be muting you because, like I've told you, I want to believe that we don't have any kindergarten here. We don't have, at times I just don't understand why people just behave irresponsibly. I have to be muting you and not participate. I will just be talking. It's supposed to be interactive. You know, so that even as I'm talking, where you don't understand, you can easily, and somebody is still there making noise, all the kuru, 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 kuru. I don't know what noise is that. You can at least mute yourself. Look, all of you, mute yourself. Except you want me to mute you from this, and you know when I do that, you will not be able to talk. You just be listening to it, and I finish talking and mute you. If that's what you like, fine. But I don't think it is good like that. So that we leave it open. Then when you need to ask questions, you mute yourself and you talk. And all that. So I was saying that, you know, from your previous learning, you have idea. You already thought about, you know, what the electrons are, how to distribute electrons, to write electronic configuration. But I just want to recap. Then we now begin to flow. We all know that every element on the we've been talking about the elements of the periodic table. We talked about, you know, as per how they were their discovery. then how they were classified, how the periodic table, the elements were classified, the different scientists who classified and what they used in classifying or what made it, not acceptable, till we got the final one of Dmitry Mendeleev that gave birth to the periodic table and the periodic law. Before, again, there was a modification by Henry Moseley that gave back to the modern periodic table and the modern periodic law. No, now we have elements, and we are told right from our secondary school that every atom of an element is made up of 3 particles: the protons, the neutrons, and the electrons.
Electron.
Who is this one that is talking? Is it Godwin Veronica? I will just, in fact, I will not just mute you. I will blacklist you from entering this class. I mean every bit of it. You have to be very mature here. What's the meaning of that nonsense? Look, I will not just blacklist you. I will not just mute you. I will blacklist you from this course. Don't think it's a joke. Should I be muting all of you like children like that? And people enter the class and you respect themselves.
Don't be annoyed.
Look, all of you, mute yourself. This, all of you, I want to see you. Usman, Dan Ladi, mute yourself. Mute yourself. Now, as we're talking, I don't want to be talking to you like this. It's not good now. Not good, please. Let's respect ourselves. So I continue. So I said, we know that the atom of an element is made up of 3 particles: the protons, the neutrons, and the electrons. And we are told, we've learned that at the center, which is the nucleus, that where we find the protons, the neutrons, and this gives us the atomic mass of an element. And again, now we're coming to electrons now, because all this while we're talking about protons and all that. For every element, the number of protons that an element has is the same number of electrons that it has, and all that. So now we're now looking at another particle of the atom. Then we now want to look at electronic distribution. And we know that it's the electrons that take part in every chemical reaction that the atom of an element undergoes to form compounds, molecules, and all that. So we want to look at electronic distribution. Electronic distribution simply is just simple, in simple terms, how we distribute the electrons of an atom in the shells. To summarize it, I don't know if you've listened to the instructional video on this course. Now, somebody is now behaving funny again. Who is asking me what page, please? Please don't do that, Zainab Muhammad. I'm not supposed to be reading your book for you. This is embarrassing. How can you be asking me what page? That's to show that you've not read. Osho Moturayo, mind yourself. So this person that is writing this, are you trying to tell me that I should be studying? It means you've not even been reading. How have you been doing your, what do you call it, your TMA? That's wrong, go. Anyway, let's continue. So, I said in simple terms, electronic distribution is just simply talking about how the electrons of the atom of an element is distributed in what we call shells. In your course material, it talks about rules governing distribution of this distribution of the electrons. But to simplify you, for you to have a clearer picture before I go ahead. You know, in our O level, in our secondary school, we were taught. Okay, let me use this PowerPoint to, I think that should be slide 10 to, I've not even shared. Okay, sorry, let me come back. Let me share. What happened here? What's happening? What is happening now? I'm trying to share this thing. Why is it saying start meeting? Start meeting what? I've already started this meeting before now. What's the meaning of this? Okay. I was trying to share. Hello, can you hear me? One person should just unmute and talk. Can you hear me?
Yes,
Yes.
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 I was at the point where I was trying to share my screen. And then, okay. Because I was trying to, can you see the screen?
Well,
The screen
yes.
Yes. All right.
yeah.
Okay.
We can see it.
All right. So let me, okay. This is, this is what you know from your O level. Showing you using these to depict one of electrons. Now you have at the center the nucleus where you have the protons and the neutrons. Then around it, about it like this, you have what is called the shells. So you have the first shell, the K shell, the L shell. The second one is the L shell. The third one is the M shell, and in all that. Now, the electrons of the atom of an element, as we have been taught right from secondary school, is that the electrons are found in the shell, revolving around the nucleus. Now, inside each shell, you have what we call the subshell, the orbitals. These orbitals just describe, it's a mathematical resolution, but I won't go into too much of that. It describes where in the shell you're likely to find an electron. And these subshell have, or these orbitals have shapes. You have 4 of them: the s orbital, the p orbital, the d orbital, and the f orbital. I come again. I said that the atom of every element is made up of 3 particles: the protons, the neutrons, and the electrons. And the protons and the neutrons are found. Usman, Dan Ladi. Usman, Dan Ladi. Yourself. What's wrong with this one? So, at the nucleus, you get the protons and the neutrons. Then about the nucleus, because the nucleus is the center where you have the protons and the neutrons. Then about it, you have shells that revolve around. That's where you find the electrons. And I said the number of protons is equal to the number of electrons. Now, you have different shells about the nucleus where you find the electrons. You have the K shell, the L shell, the M shell, the M shell. But it's not just everywhere in this shell. We call these shells principal quantum number. It is not, so I'll be using the word either shell or principal quantum number. It's not everywhere in the shell that you're likely to find the electrons. So that region, the space in the shell where you're likely to find an electron, is called the orbital. And I said there are 4 of them: the S, the P, the D, and the F orbital. Now again, because I'm summarizing this, each of the shell, each of them, the KLM, have the total number of electrons, or the maximum number of electrons they can contain. They don't contain infinite number of electrons, or they don't contain the same number of electrons. And there's a formula to quickly know this. I just pray I can get to that particular, I don't know which slide is that, where I wrote something like that. Okay, this is a formula that you use to know for each shell the number of electrons that it has. 2 times n raised to power 2. That n is the number or the position of the shell from the nucleus. For instance, now, let me go back here. This first one, which is the K shell, is the first one, so it's number 1. So it means that n is 1. So when you now substitute Techno K17, can you just mute yourself? When you now substitute that 1, it will be 1 times 1 because n squared is 1 times 1, which is 1, times this 2, that's 2. So it means that this shell whose n is 1, that's the number is 1, we take a maximum of 2 electrons, and that is exactly the number of electrons that the K shell takes. Then the L shell, which is the second one from the nucleus. So when we substitute here, because L is number 2, so it means N is 2. So N times 2 is 4. Because N squared is N times N, that is N times 2. I mean, that is 2 times 2, which is 4. Then times these 2 in front of it, giving us 8. It means that the L shell takes a maximum of 8 electrons, no more, no less, or no more. Then let's look at the next one, which is the M shell. So that is, its position is number 3. So it means N here is now 3. So when we substitute into this, we're going to have, we're saying N raised to power 2. So N is 3. That means 3 times 3, which is 9, times this 2 in front of it. That is 18. So it means that that M takes a maximum of 18 electrons. So you use this formula, I won't go further, I will just stop here, to know the maximum of electron that each shell will contain. Now again, I want to say something. Remember, I have said that each shell is equally called the principal quantum number. Each shell has, we said in each shell, it's not everywhere in the shell you can find the electron. There is a probability somewhere that you find the electron, and these are the orbitals. And I said we have 4 of them, S, P, D, F. So for each shell, it has a number of orbital 2 in it. And the number of orbitals it will have is still its position. For instance, the K, which is number 1 from the nucleus, because its position is 1, it has just 1 orbital, and that's the S orbital. The second one, L, because its position is 2, it has 2 orbitals. Then the third one, because that's the third one, it has 3 orbitals. Just like that, you continue to go. Now, as we have already, acquainted ourselves, because ordinarily we learn this in O level, as we have acquainted ourselves again about the atom of an element, the particles that make up the atom of an element, now the electrons, and where in the atom you can find the electron. You're talking about the shell, the principal quantum number, then in each shell where you're likely to find the electron, which is the orbital or subshell. We have studied, we have understood that. Now we want to look at how do we write electronic configuration? How do we write the distribute electron in these orbitals? Since we said it's in the orbitals that you will find the electrons, and these orbitals shell. How do we distribute them? So that is what our topic is all about, because we cannot be talking this if you don't understand what the electron is and everything about it in an atom. So there are a set of rules that govern, because when you understand this rule, you will be able to apply them. We have 3 sets of rules that govern the distribution of electrons in these atomic orbitals. These 2 we were taught in secondary school, because the beginning of chemistry in secondary school, nobody will start teaching you chemistry without talking about atoms or elements, compounds, molecules, all this. That's where it begins from. And from there, we begin to talk about electronic distribution. Yakubu Gamba, you better mute yourself. And Techno K17, mute yourself. Otherwise, I will ban you from entering this class. When it's time for you to ask questions, you know I always wait patiently for you to ask questions and I answer all your questions. So don't disturb. Let us learn. So we said the first one is Aufbau principle. Then the second one is Pauli exclusion principle. Then the third one is Hunt's rule. Let us take a look at what these principles are talking about and how they will assist us to distribute electrons in the orbitals. So we want to look at what this Aufbau's rule is talking about. Let me get to that slide, because not every slide I'm going to use here. Now, this Aufbau's principle, can you see it?
Yes,
one person should just, good. So we said the Aufbau's principle. The word Aufbau itself means build up. So the Aufbau principle is just talking about how you begin to build up the electronic configuration. So it's saying that electrons occupy orbitals in order of increasing energy. So it summarizes, we summarize as the order of occupancy. Now, because I'm trying to take it one after the other, I didn't want to just start telling you about the energy of these orbitals. Now, each of these orbitals, the first orbital, the least orbital, the first orbital is the s orbital, followed by the p orbital, then followed by the d orbital and the f orbital. Let me see if there's somewhere I wrote out these orbitals on their own. Oh, let's see what's this. Okay, let me use this. So you can see this. This is it, S, P, D, and F orbitals. Now, the P orbital is of three sets: the PS, the PY, the PZ. And the D orbital is 5 sets. Let me get to that. The D orbital has 5 sets, while the F orbital has 7 sets. Did somebody say hello?
Hello.
Hello, Ma.
Yes, what is it? Yeah. Say what you want to say. I can allow you to talk now. Yeah? Who wants to talk? Who is that? Now, Chief Justice, can you just mute yourself? Mute yourself, please. Then Zoom user.
Lie down there. You need dress.
Zoom
You answer
user,
me.
mute yourself. Abido Yaminat, mute yourself. Abido Yaminat, mute yourself.
Oh, sorry, man.
Okay. I'm still waiting for you to mute yourself before I start, before I continue. Now, this is the D orbital. It has 5 sets: DSY, DYZ. You have DY squared, DS squared, DY squared, and DS squared. All that. The F orbital equally have 7 orbital. I know I'm coming. I just want you to understand. And this set, because the P, the D, and the F orbital, they're just D orbital. They are just D orbital, and they're just F orbital. But because of their orientation in space, so they have different, orientation, making them have different sets. So I don't want to go much into that mathematical resolution just to make it simple for you. So we call this any orbital that have different set degenerate orbital. You know, generate, you put D in it, degenerate orbitals. Now, we're trying to look at Bauer's rule. That is slide 26. That's where we are. So I said the word about means building up, and it's saying that electrons occupy orbitals in order of increasing energy. And I said these 4 orbitals, their energies are not the same. The one with the highest energy is the F orbital, followed by the D orbital. After that, you have the P orbital and the S orbital. That means the least in energy is the S orbital. If you now put it in order of increasing energy, you have S less than P, P less than D, D less than D, and all that. Or you have it as F greater than D, D greater than P, and P greater than S. Just a minute. Are you good? You finish? Okay. So Thursday. Look, I'll see what's about. Okay. All right. Okay. So would did I got the key here? If only. No. Please ask Julius for me. Ask Julius whether he dropped it. Yeah. Or if it's on the market, but please help me ask him so that when I finish, I don't begin to look for it. Okay. So, so we have said, I've already told you. So the least is S followed by P. P is greater than S. Then D that is following P is greater than P. Then the D, after it you have the F. F is greater than the D. So I said, if we have it in descending order, we are going to have F greater than D, D greater than P, and P greater than S. So it means S orbital is the least in energy. So what our valve is telling us is that when we want to distribute this electron in the orbital, because we have said it's in the orbital that you find the electrons, you begin with that orbital that has the least energy. That is what it means in order of increasing energy. So it means you will always begin with the X orbital. And again, when you now, apart from the orbital, when you now talk about the shell, the principal, I told you another, the shell is also called the principal quantum number. You see it there in your course material. So all these shell too, they have their order of energy. The one that is closest to the nucleus, the K shell, is the least in energy, followed by the L shell. After that, the M shell, the N shell. So you will have it as N shell greater in energy than M shell higher in energy than L shell, and the L shell higher in energy than the K shell. So above wants us to understand. Okay, let's see. All right. Above wants us to understand these energy levels of the shell and orbitals where you find the electrons. So that when you understand that they don't have equal energy, then when you're distributing, you begin with the least in energy. That's what this rule is, or this principle is telling us. Because when we finish learning this, we are going to be applying them. And once you know it, you have known it. We now go to the third rule, which is Horn's rule. Because we looked at, let me come again, because I always like us to follow. so that you know where we are, the topic, rules governing the filling of electrons. And we said there are 3 sets of rules. I'm just going through this again because I like to carry everybody along. I know there might be some quick learners and some slow learners. So we're looking at the rules governing the filling of electrons in orbitals. And we say there are 3 because you can be asked how many are they. So you should know there are 3: the Alva principle, the Pauling exclusion principle, and the Horn's rule. So we want to look at, maybe we look at the Horn's rule first. And I think I have that on slide 30. Horn's rule. Horn's rule states that when electrons occupy degenerate orbitals, remember I told you what are degenerate orbitals. I said the P, the D, and the F orbitals are divided into sets. The P orbital, the P, Oladipo Barakat, can you just mute yourself? I want all of you to mute yourself. Oladipo. I don't know why you want me to be talking like this. Oladipo, I'm waiting for you.
Ma.
Oladipo Barakat, mute yourself.
Ma.
Mute your class or you leave the class. All right. So the p orbital has 3 sets, the d orbital has 5 sets, and the f orbital has 7 sets. The 3 sets of the p orbital are the ps, the py, and the pz. That is what you're seeing there. Why that of the d orbital is dsy, dyz, ds(z), ds squared, dy squared, and ds squared. These are mathematical resolutions, so don't bother your head about it, about how it is obtained and the mathematical resolution, but just understand it. Then the f orbital has 7 sets. Now, we said that these degenerate orbitals have equal energy. They have equal energy because a p orbital is always a p orbital. So you don't have that ps is greater in energy. Let me mute. Let's see. You don't have that ps orbital is greater in energy than the py orbital, or the py orbital is greater in energy than the pz orbital. No. All of them, whether ps, py, pz, they have the same energy. Then these 5 sets of the d orbital, they are equal in energy. They are just d orbital and all that. The same thing with the 7 sets of the f orbital. They are the same thing. The only ones that differ in energy, it is when it comes to the orbital itself, the sp, whatever, not those ones that are now having different sets. But p is p, d is d, f is f. So Horn's rule said that when electrons occupy degenerate orbitals, they must first occupy the empty orbitals singly before any orbital is occupied by a second electron. And all electrons in singly occupied orbitals have the same spin. So I said in simple terms, Horn's rule requires single occupancy before pairing. Because if you remember your O level, remember when you're writing electrochemical configuration, you have some orbitals where you begin to pair. So, but Horn's rule is saying you have to follow this rule. And Bell's rule, which is saying you begin with the orbital that you arrange in order of increasing energy of the orbital. So it means you begin with S. After that, you go to P. After that, you go to B. There's no way you just begin with F. No, you have to begin with the lowest one. Then when you are now in the orbital, you first of all distribute the electrons singly before you begin to pair. So it's like this picture I'm showing. Single, single, single. It is when you are finished, for example, let's say this is a p orbital that is divided into 3. ps, py, pz. You're not just say because you have 3 electrons. This thing denotes electrons, now from low level. You'll not say because you have 3 electrons. You'll now come to this first one, which is, I believe you can see my cursor there, which is ps. You now put, because we have said Okay, I don't know whether I remember to tell you that every orbital, I'm not talking about shell now, the one I was saying the one I said about 2n squared, that one is talking about the shell, the maximum number that shells can take. But each orbital, you know the orbital is found inside the shell. Each orbital takes a maximum of 2 electrons. So that's why I take time to begin to explain to you the maximum of electrons that shell will take, but I didn't tell you that of orbital. I told you what the maximum electron that a particular shell or principal quantum number will take based on, you can work it out, even if you can't remember it, work it out with that formula. But each of these orbitals that is found inside the shell, they take a maximum of 2 electrons. And what Hans rule is saying, before you begin to put that 2 electrons, you have to distribute it singly. For instance, this is now a p orbital, which is said has 3 sets, p, s, p, y, p, z. This distribute, because we're talking about electronic distribution, so this represents electrons. But you will not say because it's 2 electrons, you just come to ps, this first one here, you put 2 electrons, you distribute it 2 so that you only have 1 in the py, then the pz has none. No. Hans rule is saying, you first of all distribute them singly, single occupancy. You have to occupy single first. Let us go to Pauli exclusion principle. What does that one say? Because once you understand this thing, you can easily distribute your electron. Now, this is for an atom or an element that has 4 electrons. This is 1s2, 2s2, representing orbitals. Now, it says, why you see 2 spin, I'm using this to explain. It said, no 2 electrons in an atom can have an identical set of 4 quantum numbers. Forget these 4 quantum numbers. I don't want to take you too much into mathematics, just to simplify it for you. But what it is saying that, he said, this means an orbital can hold a maximum of 2 electrons, and then the electrons must have opposite spins, because electron spins, they spin around, they spin. That is why they have charges. Please, Fatima Yusuf Mahmoud, respect yourself. Why do people behave like this? I don't like it. I don't like it, because don't allow me, because if you allow me, I will begin to remove some of you in this class. You want to attend my class again so that we can have peace. Let those that want to learn. So I said, what this, it means that an orbital can hold a maximum of 2 electrons, which is what I've told you. And then the electron must have opposite spins. If they spin in the same direction, you all did physics and all those things. If they spin in the same direction, they will be repelling each other and all that. And of course, that atom cannot hold, it cannot be stable, but they don't have to do that. So that's why they have to spin in opposite direction. So that is what Pauli exclusion principle is saying, and that is why you have in this distribution, this is for an atom that has 4 electrons. This is beryllium. This is the electronic configuration. So the electrons, yes, each of these orbital takes a maximum of 2. But when you're even going to put them in that orbital, they will not be facing direct the same way. The electrons have to be in opposite direction. So we use this to depict the electrons spinning in opposite direction. So that is what Pauli exclusion principle is saying. So the first one about principle talks about you begin to distribute the electron from the lowest orbital to the highest. Then, as you're doing it, Hans rule, put them singly. Then when the electron remains, you can now begin to pair. So when you now begin to pair, you now remember Pauli exclusion principle, where you begin to pair them in opposite directions so that they spin differently. So in simple terms, these things are in your book, but they might be too too much grammar there. This is in simple terms what it is talking about. So with this one, we want to look at some worked example. Now I have nitrogen. Nitrogen has atomic number of 7. And remember I told you, remember that atomic number means proton. I said every atom or every element, the number of protons is equal to the number of electrons. So if it has atomic number of 7, it means it has 7 electrons. Because on the periodic table, these elements are arranged in atomic number. What you'll be seeing is the periodic is the atomic number. You'll not be seeing number of electrons, it's atomic number. That's what is written on top. But you have to know that every atom, the same, the number of proton of every atom is equally the same number of electrons. So since nitrogen have atomic number 7, remember the last time we had class I said atomic number is represented by Z. So that will write Z equals to 7. So it means it has 7 electrons. So if we have to write the electronic distribution, we begin with Abba's rule. Now, let me see if I can write somewhere here. Or this is drawing this thing now, so that I will now. But let me just go ahead to use this. Now, Abba's principle said begin with the arrange in order of increasing energy. It means you begin with the lowest energy. And remember that we said the electrons are found in the shell, and in the shell you have the orbitals. We have this figure in front representing the shell. That's why I started telling you, like the K shell is the first one, number 1. The second one, the S shell, is number 2. So the orbital, we have to carry the number of its shell. Now, we begin with the first shell. The first shell is number 1, the K shell. And remember the maximum number that's why I started teaching you that first shell, the K shell, will take. If you can't even remember, use n2 n squared. So since it's the first, the number 1, n times n, because n squared is n times n, and n is 1. 1 times 1 is 1. Then times the 2, 2. So we have already studied. I'm just recapping and saying this again because of carrying along some student learners. So who is that one that is talking there? So this first shell, we have a maximum of 2 electrons. And the only orbital that is found there is the S orbital. Remember again, I told you that the number of orbitals that you find in a shell is just its position. If it is the first shell, then it's 1 orbital. If it's the second shell, like L shell, because it's second, it's 2 orbitals. If it is the third shell, because it's number 3, it has 3 orbitals, SPD. The one that is 2 will have 2 SP because you begin with increasing. So this one that has just the K, that is just 1, and has 1 orbital. And that orbital is the least one, S. So that is why you're seeing just S here, because it has just 1 orbital and it takes a maximum of 2 electrons. So we put X, then to designate the particular shell we're talking about, we put 1 in front. So it makes everybody, any scientist, to know that this one S you're talking about it because you have all these orbitals, like S orbital in all the other shells. You're talking about the S orbital of the K shell. So that's why I have 1 S. And we have said both the S orbital and the K shell takes a maximum of 2. So these 7 electrons of nitrogen, we first of all put one direction. Now you can put another because it must finish with that energy level before you go to the next energy level. So you can now pair. And remember Pauli exclusion principle. You pair in opposite direction. So you write it like this. Then you have distributed 2 electrons like this. It is remaining 2 minus 7. It's remaining 5. So it means the 5 is going to the next shell. And that next shell, remember it is, you can work it out. N is 2 because the next one is the second one. N is 2. N squared. N is 2. So 2 times 2 is 2 times the 2 that is in front. 2 times 2, sorry, is 4 times the 2 that is in front. 8. It means that that shell takes a maximum of 8 electrons. Now, what is the number of orbitals it will have? Ask yourself. Because it is number 2, it will have 2 orbitals. And what are those orbitals? Because it has to begin from the increasing order to have the s, and the one that is following it, the p orbital. That's what it has. Now, that remaining 5 electrons, how do you distribute it? You now come. Remember, of Bohr's principle, you begin with the lowest energy orbital, which is the s. You have to fill it up before you do. So that one, the s orbital, we have said that each orbital can take a maximum of 2 electrons. So s orbital will take that maximum of 2 electrons, which you have to fill first. So you put it first, then the second one, put it in the opposite direction. You have obeyed Pauli's exclusion principle like that. Then now you have put 2 out of that 5, remaining 3. The 3 will now have to go to the p orbital. Remember that the p orbital is divided into 3, ps, py, pz. That's why you're seeing all of them, p here. In many instances, ordinarily I should have written 2ps, 2py, and 2pz to differentiate them, but I've already explained it, you know. Now you can see that in front of this s we have 2. This 2 is showing that this s orbital is the one found in the second shell. That's why you have that 2, second, number 2. Then the p, you have 2 in front of it, showing that it's a p of the second shell. Now, remember what, because we've just followed our Bohr's principle, distributing that 5 electrons in order of increasing energy. That's why we started with 2s, we filled it. We are now going to the next one, which is p. Remember, s is higher, p is higher than s. So we come to p to put that 3. First and foremost, we remember Horn's rule, because you follow them sequentially. Our Bohr's principle, order of increasing, whatever, then Horn's rule, which is single occupancy. You will not say because it's 3, you now put this one here, you now pair it, the other one in opposite direction, then put one here and do this one. No. You first of all put 1 in the first, which is 2px, the second one, 2py, then the third one, 2pz. You fill them singly. Then in that way, we have distributed this electron. So this is the electronic configuration for nitrogen. I want to take another one, oxygen, so that to help us to understand. Oxygen has an atomic number of 8, so it has 8 electrons. So if we're to distribute it, we begin with the orbital in the first shell and maximum of 2 electrons, both for the orbital, because the K has 1 orbital. I've already explained why it has 1 orbital. So as we put the first one, then Pauli exclusion principle, opposite spin, put that, put the s, and we put 1 to denote that is for the, to denote that it is for the first orbital. Then the second, now that means 2 minus 8, leaving us at 6. Remaining 6 electrons goes to the second shell. And the second shell has 2 orbitals, s and p. Now, we begin with x, because s is the lowest in energy. That's arranging in order of increasing energy level, our Gauss principle. So we come to the s orbital. We have to put two in front to designate the shell we're talking about. We put down maximum of 2 in opposite direction obeying Horn's Pauli exclusion principle. We now, the remaining, we have removed 2 from the 6, remaining 4. That 4 now goes to the, because the s orbital is filled up, now goes to the p orbital. P orbital has 3 sets, py, px, py, pz. First and foremost, what happened here? It was filled singly, as we did here. Filled singly, 1, 1, 1. That was what happened. Filled singly, because we're left with 4 electrons. So after filling this singly, we have 1 more electron remaining, the 8th one. We now can begin to pair. So that is what Horn's rule is saying. Fill singly. After that, you can now begin to pair. So that one that is remaining, the 8th one, we can now begin again from the first one, PS, or put it in opposite direction to obey Horn's rule. So that is how electronic. So with that, you can feel, you know, no matter the electronic configuration, even when the electronic configuration is 100, you can be able to do it. Just simply follow the rule and all that. I want to go to something before I now come back, because I have feeling of 1 electron of a higher atomic weight. I bring you to this. This is orbitals in different shells. They have the 1, which is K, the 1, the 2 representing the L, second one, and you have all of them like that. So this is how you feel in order of increasing energy. 1s, 2s, 2p. After that, 3s, 3p. Ordinarily, you should have 3b, but before you have 3d, you have a 4s before the 3d. Then you now have 2p. Before you begin to have your 4, after the 3d, you have your 4p. Before you begin to have your 4d, you have a 5s. Then you now have 5p. So I don't know. If you listen to the instructional video, you will see this. You'll be able to copy it out, because I don't think you can be able to quickly copy out this. But then you can always, it's there in your course material, the order of filling of these electrons based on increasing energy level and all that. Now, once you're able to know this, you can now use it to begin to fill your electron. I want to go to, I think I worked on the bromine, one of those ones with heavy. This is electronic configuration of bromine. Bromine has atomic number of 35, so it means it has 35 electrons. So to fill this is how it is filled. Of course, 1s, 2s, 2p, 3s, 3p. After 3p, you have 4s. After that, you have your 3d. Then you now have 4d and all that, 4p and all those other ones. So if you know this order, the other ones have shown you, you can, go to the periodic table, take any element there, try to write out its electronic distribution following these 3 rules that I've shown you. But you have to know those orbitals, how they are arranged in order of increasing energy level. So we want to look at, remember I told you that this unit 3 has 3 subheadings. The first one is rules governing the filling of electrons. Now we want to look at electronic, so we use those rules to write the electronic configuration of atoms of an element. We want to look at electronic configuration of ions. From our O level, we have idea what ions are. We know that ions are either cations or anions, and that cations have positive charge. And they are formed when an atom loses electron. Then the anions, carry the ones that have negative charge, are formed when atoms of an element gains electron. Equally, as we can distribute or write the electronic configuration of atoms of an element, we can equally write electronic configuration of ions of charged substances or of ions. Let's put it like that. You can write the electronic configuration of cations. You can write the electronic configuration of anions. We want to look at some example, like calcium. Calcium has atomic number Z of 20. It means it has 20 electrons. And when we write the electronic configuration 20 to be like this, 1s2, 2s2, 2p6, and just in this order, following the order I've shown you before. When you check it, it adds up to 20 electrons. Now, calcium is in group 2 elements. It's in group 2 of the periodic table. When it loses electron, it loses 2 electrons. So if it has 20 electrons and it loses 2 electrons, it means it will now, its cation. Let me look for its cation. Its cation, which is Ca2 plus raise, is 18 because it has lost 2 electrons. So it will now, the calcium ion or the calcium cation, we have 2 electrons. We equally distribute the electron of this calcium cation just the way you distribute the electronic configuration of its atom. And look at this. If you look at, the calcium atom, you can see that the last electron is in the 4s orbital, 2 electrons there. So it means the electron that it is losing is from the x orbital, and this s orbital, from what we're seeing here, has 2 electrons. So it goes. So if it goes, it means there's no more electron in that first orbital. So it means the electronic configuration will now stop at 3p, which is what we are having here. 1s2, 2s2, 2p6, 3s2, and 3p6, because this one now is the calcium cation. Because you can be asked, write electronic configuration of maybe compound X, then loses how many electrons, write is the electronic configuration of his ion, so that you'll be able to understand and all that. This one is for cation that has lost electron. You equally have a situation whereby the atom gains electron. I use example here, chlorine. Chlorine is electronegative. It normally gains electron. And it has atomic number of 17. When it gains electron, it normally gains 1 electron. When it gains electron, to gain 1 electron, so its anion, chloride ion, will now have 18 electrons. For this neutral atom, this is the electronic configuration 17. But when it gains electron, because it gains 1 electron into the p orbital, because it is the outermost orbital that takes part in reaction. So that is where the losing of electron and gaining of electron happens, the outermost orbital. So as it gains this 1 electron, it will gain it into the outermost orbital. So it enters the p orbital. and you now have it as 18 electrons there for the chloride ion or chlorine anion. Before, anyway, let's just round up before we take. I want to say if you have a question, you can ask. Now, we want to look at the last, subhead in this unit 3, which talks about distribution of the elements into blocks. Electronic configuration and division of elements into block. We've said we have 4 orbitals, S, P, D, and F. So elements are distributed into S, P, D, and F block on the periodic table. We have what we call the S block element, the P block element, the D block element, and the F block element. It's not difficult, it's just simple. That block they are talking about is designating or meaning that those elements where the particular orbital where the valence electron is, valence electron from your O level means the outermost electron. This thing is from your secondary school. They've been teaching you valence electron, atoms, all this. So this one is just, we're just repeating the same thing. So the valence electron are normally found in the valence shell, the valence orbital, or the valence shell. We have said what orbital is, we have said what shell is. The only thing I've not talked about valence. Valence means outermost. So we're just talking about the outermost orbital. Now, look at this example. This is group 1 element. I take the first 3 because I can't come and start working on everything there. The first 3 elements there after hydrogen. You have lithium, Li, sodium, Ni, because you have to know their symbol, potassium, K. And the atomic number of this lithium is 3. The atomic number of sodium is 11. The atomic number of potassium is 19. When we write the electronic configuration, lithium is 3. So you have 1s2, 2s1. For sodium, it's 11. This is the electronic configuration. For potassium, it's 19. This is the electronic configuration. So if you look at these 3 elements, you will see that the valence orbital is S, the S orbital. So, and the valence electron, that's the outermost electron, this one you're seeing, they are in the S orbital. So it means this element will now be S block element. So we're saying that you designate this element into block depending on the orbital where the valence electron is. That the outermost electron, the orbital it is found. If it is S, it becomes S block. If it is a P orbital, it becomes a P block element. If it's a D orbital, it becomes a D block element. If it's an F orbital, it becomes an F orbital. The same too like group 2 elements. You have the beryllium with atomic number 4, magnesium, atomic number 12, then calcium that we just with atomic number 20. This is the electronic configuration. You see that these, their outermost electron, which is just 222, they are all in the S orbital. So they are S block element. Let's take a look at another example. This is group 13 and group 14. Now I have the first element. If you go to your periodic table, check it. P. The B there is boron. So the element boron, it has atomic number 5. Then the Al is for the element aluminium. It has atomic number 13. Then the Ga there for the element called gallium. It has atomic number 31. So when you write out the electronic configuration, this is what you have. And you have that the outermost orbital is the P orbital. And the electrons, the valence electron, the outermost electron are in the P orbitals, which are the valence orbital. So now, because this valence electrons are found in the p orbital. They are all called the p block element. The same thing with group 14. You have the first one there, carbon. The second one, silicon. Then the other one there, germanium. This is the atomic number. This is the electronic configuration. Their valence electron, which is 2 to each, are all in the p orbital. So they are called the p block element. So for the d block element, once the outermost electron are in the d orbital, it becomes a d block element. The same thing with F. If the valence electron of those elements are in F orbital, they become an F block element. Now, I just want to go to the periodic table so that you see how these elements are divided into blocks. Now, group 1 and 2, their valence electron, their outermost electron are in the S orbital. So they are called the S block element, denoted by green there. Then for group 13 to 12, their valence electron are in the D orbital. So they are called the D block elements. Then for group, the other one is group 3 to 12. Then for group 13 to 18, their valence electron, their valence outermost, their outermost electron are in the P orbital. They are called the P block element. Why, as when we, remember the last one when we looked at the periodic table, we looked at those ones that are outside the lanthanized and actinized. Why these elements, lanthanized and actinized, their valence electrons are in the F orbital. So they are called the F block element. But you have some of them too, that the valence electron are in the D orbital. You have them as the D block element. So that is just the simple thing about division into block. There's no big thing about it, just talking about, division of this element into block based on the orbital where you find the outermost electron, which is also known as the valence electron. So that is that. With that, we have come to the end of Module 1, Unit 3. So let's take some questions so that we can call it a day. I'm sure it's up to...
Yes. My first question, ma.
Yes.
Yeah. Thank you very much for the explanation. It's quite, it's a long time, but I'm able to understand very well. So my question is, how do we help us classify, like one S, it is SDPF, right? So how do we know, S
SPDF.
Yes, S houses one molecule, right? One molecule.
No, not molecule. We are not talking molecule. Electron.
Atom.
Electron.
Okay, electron. So S houses two electrons maximum.
Max. Yeah.
Hey, Titus,
Yes.
Titus, mute yourself.
Yes,
Mute
So
yourself.
D. So how many electrons does D, P, and F have a house? So we just understand that here.
I said S is 2 electron maximum. The P orbital total is 6. See how it is 6. Remember, I said like the P orbital is divided into 3, isn't it? You understand that, eh? Do you understand that? Yes. It's divided into PS, PY, PZ. I didn't want to start going into too much. I just want to simplify this. So that's why I didn't want to start showing you the orientation in space to see how you begin to get PS, PY, P, whatever, because I just want to simplify this just for easy understanding. So I'm just trying to look at the orientation in space. This is the P orbital, oriented as PS, PY, PZ. But forget about this one. We don't want to go into too much grammar. You understand? Let's simplify things. So I'm just coming back for you to know why the P orbital is divided into 3. It's because of the orientation of P orbital in space. It's into 3 places. So we said it has 3 sets. Each of those sets take a maximum of 2 electrons. PS takes a maximum of 2 electrons. PY takes a maximum of 2 electrons. PZ take a maximum of 2 electrons. So when you add them together, P generally now has 6 electrons. Then for the D orbital, remember, look, this is the D orbital. This is its orientation in space into 5 places and all that. PSY, DSY, DSZ, and all those things. So let's just leave that one to make it easy. So the D orbital is divided into 5. And we have said each of those, we call it degenerate orbital. Each of those degenerate orbitals takes a maximum of 2 electrons. So the SY, 2 electrons, the YZ, 2 electrons, and like that into the 5 set is divided into. So when you add it, you give a maximum of 10 electrons. Then the F orbital, 2, is divided into 7 orbitals. So each of those 7 orbitals, each of them take maximum of 2 electrons in 7 places, giving you 14 electrons. So the F orbital takes a maximum of 14 electrons. I don't know if I've answered your question.
Yes, ma. Yes, ma. Thank you.
Okay. Michael, let me just begin from up as I'm seeing it here on my own side. Michael Agaba.
Yes, ma. I just want to ask about the recording because your class actually classed with physics. So I just left physics now to join this one.
Oh.
So how can I get this recording?
How did the timetable be like that?
Honestly,
I think we have to resolve
class right now. Yeah.
Yeah, we have to look for a way and resolve it at the faculty. That's not good because it's not good to meet any class. Well, we're both chemistry and physics, they're both in the same faculty of sciences. I think I'll discuss with them at the physics department so that we'll know what to do. So that
all right, thank you.
So ahead, you talked about recording. Yes, if you go to the platform, to the virtual learning environment, the eLearn platform,
okay,
you will see that the first class we have, I've pasted it there. The link, because what you'll be seeing is link and the pass code is there. The second one too, you will see it, the link and the pass code. This one now, as we're doing it, is being recorded. So at the end, when I end the class, in the next 1 hour, Zoom will send the link and I will paste it there so that you can go and listen to it. But I will see a way how we can resolve that clash because it's not really good.
All right, man. Thank you very much, man.
You're welcome. Ahmed Fadimatu. Ahmed, you're raising up your hand.
Okay, good evening, ma.
Good evening. How are you?
I already you have already answered my question. Somebody asked you.
Oh, okay.
I forgot to lower my hand. Sorry.
Okay, no problem. So I go to Insikat Ian.
Yes, ma'am. Good evening, ma'am.
Good evening.
Yeah, it's Nsikag Ian.
Yes, I called you now.
Okay. Please, my question is when we were explaining about an element losing electron.
Yes.
What causes it to lose electron? Is it that it is not balanced? That is why it's losing the electron. Please, can you explain further now?
Okay, now we want to go to chemistry. You see, remember that when I started teaching this course, I told you that everything that we have in this world is made up of elements. Those elements in the periodic table, many of there's, assuming, I want to believe you did chemistry in your own level. Remember that we said that every element of the periodic table try to attain stability by attaining what we call the octet rule or doublet state. Once the valence shell or orbital is not filled up, it will continue to react. And it reacts in 2 ways, either by gaining electron or losing electron to form ionic bond, or sharing electron by covalent bond and all that. The only elements in the periodic table that are stable, that don't undergo all this gaining or losing electron or sharing electron, that are stable and they are highly unreactive, is the noble gases. The noble gases. But apart from those noble gases, like argon, neon, krypton, and all that, xenon, and all those things, apart from those elements, all other ones, they are not stable. So they are trying to attain stability. And the only way they can attain stability is either by gaining electron or losing electron. Okay. So see, I'm with your physics teacher. Don't see here. Come. Let's resolve it here. Because I was telling them that you and I, we are from the same faculty. Just finished teaching them. They said our course is clashing. Physics, is it physics 1 something you're thinking?
No, it's physics 101.
Oh, 101. Who is taking 101? So you took them over there.
No, ma'am, I think, ma'am.
Okay, Dr. Banga.
Yes, ma'am.
Yeah.
I think what really happened is he apologized. He started the class late. So it's not that it ought not to clash. We started at 4 p.m.
because you
and we're supposed to end at 5. Yes, it started late, so that was what happened.
Okay. So that's resolved now.
Yes, ma'am.
Oh, Wahala.
Thank
No,
you.
drop it. I think I've gone with my things. Thanks. I will soon leave. All right. Okay, no problem. I thought the timetable is like that. That's why I said we are all in the same faculty. We are one family. Can always be resolved. No problem. But I will talk to Dr. Banga so that it doesn't, start late.
Please, Madu.
So that one will be resolved. Don't worry about it.
Okay, ma. Thank you very much.
Okay. So, I was answering Isikat. So I've told you why. That all those elements you're seeing on the periodic table, apart from the group 18, the last one, as those last of the group 18, they are called the noble gases. Noble because they are calm. Their electrons, the orbitals are completely filled up. And all that.
They are humble.
Look at this. Let me go to okay, no. That's below. So that you understand what I'm saying. I want to go to this one I use in teaching you block and all that. So that you will see. For instance, look at these group 1 elements. You see that the s orbital should take a maximum of 2.
Yeah.
It's not complete. If it is not complete, it can never be stable. It will keep on trying
losing electron or gaining electron.
Losing electron, gaining electron. This one too, look at them, the p orbital. The p orbital should be 6 maximum. This one, this particular group 13, they have 1 each. So they are short of 5. They cannot be stable. The same thing with group 14, they are short of 4. So far, these elements, all of them in the periodic table, once their outermost orbital is not filled up, having the number of electrons that it requires, it can't be stable. So it will continue reacting either by losing electrons, gaining electrons, ionic bonds, stable, or sharing bonds with other atoms, covalent bond to become stable. So I've answered that. Who is the next person? Titus.
Yes, ma'am. Good evening, ma'am.
Good evening. Welcome.
Thank you, ma'am. But please, my question is, I think it's a bit out of what we're talking about. I just want to ask about the instructional videos, ma'am. If you can upload also that.
Is there now the instructional video for this course here, NOUN from beginning of the topic, module 1 to the last step? Is there on the
because on my own page I'm seeing only 3 this thing. I want to stop at I think hydrogen.
You're seeing only 3 what?
Yes, ma'am. It's not complete.
My own stop at hydrogen.
I don't know. There are 24 videos there. Okay. There are 24 videos. Anyway, since you've complained, I'll go to the directorate that is in charge, Directorate of Learning Content Management, and know what, because it's a complete video, 24 videos.
Okay, ma'am.
So
thank
since
you,
you've complained, tomorrow is a public holiday. On Thursday, I'll see what to do. All right. Usman Danladi. Usman Danladi.
Okay, ma. The last example of chlorine that you write the atomic mass.
What happened to atomic mass?
The electronic configuration of chlorine, you give the example of it.
Yes. I use it as
I count the electronic configuration is 18, not 17.
No, chlorine.
So how can
excuse me?
okay.
It means you are not listening. I gave you electronic configuration of chlorine as the chlorine atom.
Yeah.
Then I gave you electronic configuration of the chlorine anion, chlorine or chloride ion or chlorine anion, which is 18 because the chlorine gains one electron to become 18. Remember, that was under the topic of electronic configuration of ions. So have I answered your question?
Okay.
Do you understand now?
Thank you.
Yes, that was let's go there because I always like to. Where is that that's on the electronic configuration of this is it. Here we're talking about with that one, you would mute yourself. Usman, mute yourself. You cannot be listening like that. So we're talking about the electronic configuration of ions. So let me go back to the chlorine that you were talking about. This is the chlorine atom, the neutral atom. Neutral atom, it has not gained an electron in any way. So we're now talking about when it gains electron to become the chlorine anion or the chloride ion. And it gains one electron. It gains one electron into the outermost orbital, which is the p orbital. And because it gains one electron, 1 plus 17, is it not 18? It becomes 18 electrons. So that's that. Folorunsha.
Yeah, thank you very much, ma'am. Very good, ma'am.
You're welcome.
Yes, ma'am. My question is based on the practical that we had to have. And we really appreciate you actually enlightening us that the practical will be starting on the 3rd of October, which yeah, which we can see the timetable now. But the timetable is somehow confusing also. Like, so we want you to probably shed more light on it, on how the practical will be run, man.
What's your study center?
VI, man.
VI.
Lagos, yes.
Now you know that it's a faculty thing. So we have our practical at the same time. So you're going to have chemistry practical, physics practical, biology practical, computer practical, and mathematics practical. Mathematics, they will teach you how to use equation editor, all those things to write symbols. Computer, many of you here are computer students. To do all those things, you do all those your programming or all those your kind of a thing and all that. So they have to do that timetable. You see chemistry, how many hours? Physics, how many hours? No, just so that's it. They just did it like that to capture every course that is going to be there. But I even know that of Lagos might be different because that's where they have the highest population. They might do it in a way to suit you people, but for now, that is the general timetable to accommodate every course that will be taken. Because we equally have 200 level practicals to accommodate all of them. Okay. And the practical now, remember, is all the practical courses. Now, you have some people that will do, which practical course are you doing? Is this CHM191 or 192?
191.
So you'll be doing 191. Some people are in second semester. Some people are doing 192. So maybe that's why you're seeing things like that.
Okay. Thank you very much.
You're welcome.
I really appreciate it.
You're welcome. Samson Lona. Samson.
Yes,
Lona. Yeah.
Good evening, ma'am.
Good evening. Welcome.
Actually, I wanted to ask for that for the instructional video.
It's on the eLearn platform. But since you say you're seeing only, I don't know what they say, but I will check with the rating of learning management content because it's supposed to be 24 videos. So I will check. I know exactly what you said.
Excuse me, ma.
Hmm.
This is my first time being here because I've been having problem with my email and everything like that. So that is the reason I wanted to know if instructional video is available for when you
The
guys can
instructional
take.
video is there. Then the classes you might have missed, the first and the second, I've pasted their link and passcode there. You can go and listen to them.
Thank you.
All right, you're welcome. Then Miracle Victor. After that, I'll just take one more question. I call it a day. So Miracle Victor, please be fast.
Yes, good evening, ma.
Good evening, welcome.
Okay, thank you for the lectures. Please, my question is on the practical timetable. I don't really understand the date settings because
See the date there, and it's starting October 3rd.
Yes, it's starting October 3rd. October 3rd is a Tuesday, but we are having practical on Monday. I'm seeing Monday.
No, it's not starting on Monday. You have to follow Tuesday. Follow the date. The one that is follow that one. So Emma, is it Adia Peter something? Be fast, please, because I want to end. Time has gone. Yes. Peter Abba.
Yes, ma. Good evening.
Good evening. Welcome.
Thank you, ma. Sorry, I'm a bit in a noisy place, but regarding the practical, that's when I think coming, ma.
You say what happened to the practical?
The timetable said, I think there's a class because I saw chemistry 191 on the same thing applies to biology. Bio 191 is appearing double. I don't know why.
Yes, you take it, just follow the timetable the way it is. There's no mistake in it. Follow it the way it is. Then
so we are doing the practical double. We are doing the practical twice or what?
It's not one practical now, bros. We have different practicals for
That's what I've explained.
For the same subject or course now. So
Emmanuel De Santos, so that we can leave here.
Good evening, ma'am.
Good evening.
Ma'am, about this configuration you explained. Now, you said that this one, because that S orbital has 1s and the second orbital is 2s. Now, the same thing is applicable, but when it gets to P, it's not starting from 1p, it's starting from 2p.
Now, how many, the first shell, what's the first shell?
The first shell is S shell. That's the K.
I'm not talking about orbital. I'm talking about shell, the principal quantum number. The first shell from the nucleus is what?
K shell.
The first shell from the nucleus is what?
K shell, ma.
K shell. Then that K shell has how many orbitals?
Just two.
How many orbitals does the K shell have?
It has two.
It has one orbital. It has one orbital. Listen, I told you that each of those shells, their number from the nucleus, to help to make it easy for you, designate the number of orbitals they have. Now, from the nucleus, the K shell is the first. So it has one orbital. From the nucleus, the second shell is L. Because it's second number 2, it has 2 orbitals. Now, we have said that K, which is the first shell, has 1 orbital. And according to our past principle, we said we begin with order of increasing energy level. If it has one orbital, so it will begin with the lowest one, which is the s orbital. So that's why it has only one orbital, which is the s orbital. So you cannot, there's no p orbital in the k shell, in that first shell. So that's why it does have it as 1s2. Then you didn't even ask yourself, now, the one that has 2s, 2p, why doesn't it have a 2d or a 2s?
Yes, ma'am.
Yes, the second shell has 2 orbitals. And beginning from the increasing energy level, you just have, after S, you have P. So it stops at there, S and P. And like that. Then the third shell, because it's number 3, it has 3 shells. So that 3 will now be what? Those 3 shells will be what?
SPD, ma'am.
Exactly. That's it. And we have said you use that, you write the number first to designate the shell we're talking about. So I believe we can call it a day now.
Okay, ma'am. Thank you very much, ma'am.
Thank you. And you know, this is just the 3rd class.
Yes, ma'am.
And this is week 1. I didn't start on time with you people. Used to, as I told you, circumstances beyond my control. So how are we going to make up?
Okay.
Ma, we can fix.
We can have additional class now.
That's what I'm saying. When?
Yeah. But I'm thinking of
Thursday.
to 17. That 3rd to sister, I can still go maybe once in a while. That 17th
We can fix additional classes by weekends, man.
Okay, by weekend. When on weekend?
Friday.
Saturday preferably. Saturday.
Saturday.
Saturday preferably.
Okay, Saturday in the afternoon. So what time in the afternoon?
We don't have class on Friday.
Saturday is filled though.
Let's make it Saturday.
Saturday is filled though.
Ma'am, Saturday is
3
always
p.m.
I think Friday.
There are other courses on Saturday. There are other courses on Saturday.
Okay, so we see on Friday then.
Friday, man. Yeah,
Friday,
What
3
time?
p.m. 3 p.m.
No, they are planning on Friday 3 p.m.
So what time, please?
In the morning.
Friday by 8.
So by what time?
Excuse me, ma, just choose the time for us. But Friday is
8
fine.
p.m. ma.
Friday
Give
is
us
fine,
time.
but just give us the time. But Friday is fine.
Somebody is saying 8 p.m.
Yes.
Okay, man, let us go with 8 p.m.
Is it okay? 8 p.m.
Yes, 8 p.m. is
Yes,
fine,
ma.
ma'am.
8 p.m. is okay. Friday.
Okay.
Yes,
Just
ma'am.
write it down.
Yeah,
Thank you,
All
ma'am.
right
yes,
then.
ma'am.
8 p.m. Friday. Let me just write it too.
Yes, ma'am.
Yes, ma'am. Thank you, ma'am.
All right. Okay then. See you then.
Bye, ma'am.
Bye.
Please, ma, before you go, can I ask something, ma?
Yes, do that quickly.
Please, ma. I'm a computer science student, 100 level. I don't know, how do I get my course materials?
From your study center now. Didn't they give you at your study center?
No, I was not given.
I wasn't even given one.
They gave me one.
They didn't give me one.
Most of
What you
don't
do?
have course materials.
You can get the soft copy. Go to NOUN courseware. Are you listening to me?
Yes, ma.
Go
Yes,
to
ma.
NOUN courseware. When you go to NOUN courseware, you see all the course material. Or if you know under your maybe your course registration form where you register this, if you know all the courses you're offering, you can just type. You can just go to Google, put CIT. Let's say maybe let's like this course now. CHM101 NOUN courseware. Enter it to bring it out for you. I mean, I'm just talking about the soft copy. But ordinarily, your study center should give you the hard copy. But while waiting for the hard copy, you can get the soft copy. You can even download it on your laptop, phone, but it might be too heavy for your phone, but your laptop. So like I said, for example, like this course, now you can just go to Google, just say CHM101 NOUN courseware. As you do that, it will bring it out for you.
Okay. All right, ma. Thank you, ma.
Good night. Okay.
Mama, one more question.